just wanted to ask you a question about free will. How compatible are A to D with free will?
A, I think it's pretty obvious that there's no free will involved in this. In the standard interpretation.
I think you've got a problem also with free will. You could relate to emotion, saying that you're actually reacting to something before it actually reaches your brain, which effectively the human brain would do. So it's a much larger question.
Yeah, it is. So I'm not sure what the model of free will is in this system.
Well, I
We all think we have free will, but
and
when we do
determinism, the problem of free will and determinism. And I can tell you that it can be argued either way, that free will happens in a deterministic system, so we're self-determined, or you can argue that we need randomness for it to be free will. So this can take a lot of discussion before we really work it out. So I don't think we should discuss it now.
Okay.
Martin's welcome. Martin's going to come back in a few weeks' time and lead us to the discussion on it.
Sorry. Well, I also know something about AI, so I'd rather talk about that.
Okay.
I was just going to say one thing. You can imagine a really crassly physical universe where there's nothing more subtle than an atom, and all thinking is computation, but where free thinking is also everything's not determined. These are not mutually exclusive notions. So it's a tangent.
Okay.
So this is Penrose's list, isn't it?
That could be broken up into, I guess, two main sub-viewpoints. One of which is that this is also deterministic, and one of them is that it's non-deterministic, perhaps. Okay. So I just basically mentioned the last point, which is that no physical processes that occur in the universe, we know it, underlie consciousness. So this is the idea that consciousness is completely outside of the physical realm. We can never simulate it computationally, and indeed, physical processes themselves cannot even simulate it.
Is that like magic?
It's like the mystics' viewpoint, for example.
Like electricity 200 years ago.
It could also be phrased, as a case of whatever it is, we can't measure it. We don't have a scale that will weigh consciousness. Which you could also say, things like neutrinos, incredibly light, don't interact with.
Yeah. Okay. So okay, a show of hands.
In reverse order.
In reverse order. Okay. So D. 1, 2.
Ooh.
Okay. Who thinks C? Okay.
Yeah, maybe.
So 5, 4, 5. Who thinks B? Oh, that's interesting. Maybe 1. Half. Okay. And who thinks A?
Well, I said maybe. That's why I asked.
So that's just quite an interesting experiment. So I just thought I'd talk a little bit more about viewpoint C, which is basically what, this is how it ties in with quantum computing, because viewpoint C is compatible with the idea of the quantum computer, the brain being a quantum computer. And this is actually the viewpoint put forward by Penrose and Hamroff in their orchestrated objective reduction model of the brain. And what this means, quantum processes are well enough isolated and shielded from the environment, then they can happen, they can occur in these structures. Now, I don't believe this is true, personally, for two reasons. The first being, like we said, the brain is hot, so there's lots of thermal noise, there's lots of stuff around, so there's other interactions all the time with the environment. For example, we can do EEG and MEG scans of the brain, which shows there's so much electrical and magnetic activity going on in the brain. This can couple into almost any quantum system and disturb it. So this is another reason against getting a macroscopic quantum coherent state. And also the other one is what we just said, is I don't personally think that you need quantum effects to explain consciousness, but that's a personal opinion. Whereas this is fact. Okay, so quantum consciousness. So even if the brain is classical, regardless of what viewpoint you take, could we potentially build a quantum brain then? And what type of consciousness would it have? The real limitation to building a quantum brain is this question of how big can you build a quantum system? And as far as I know, there are no fundamental limitations in the current theory of physics to building a quantum system of any size. The only problem is, in the real world, you have decoherence. So if you could get a quantum system that was perfectly isolated from its environment, then you can maintain the coherence. However, in the real world, keeping anything away from the environment as you make it bigger and bigger becomes a harder task. So this is really an open question in physics, is how big you can build quantum systems. And this is why these superconducting flux qubits are quite useful, because these are already quite big in terms of quantum systems. And the idea is that we want to develop them so that we put larger and larger numbers of them into quantum superpositions. And this is a way to get from the small scale into the macroscopic real world, is by just adding them one at a time or 10 at a time and seeing if the quantum coherence is maintained once we've got rid of the other problems that we find from decoherence. So the question is there any other fundamental limit, if you take away all the problems with decoherence, that stops you from building a big quantum system? And the real key point is here, we don't see macroscopic quantum objects, okay? We don't see a person in two places at the same time. And the question is why? Is it just decoherence, or is there something more fundamental? If there isn't, then we should be able to engineer these systems. So one other thing that's again being proposed by Penrose is that the limit on quantum coherence in macroscopic systems might be because of the mass. If there's some mass or gravitational interaction that we don't understand, as the system gets bigger, then the mass in itself might cause decoherence. But again, this is just a theory. It's not. There's no evidence for this at all at the moment.
Sorry, just to wait a minute, there's sort of a clarification.
Mm-hmm.
Penrose has sort of got this crass model of quantum consciousness, in my humble opinion, where, he's talking about superposition of states across large sections of your brain, whereas there's a more subtle way of imagining that there might be quantum roles to play in, basically, we know that different parts of your brain have different functions, some of which, in sort of especially the visual areas, are quite reasonably well mapped out now. And we know that all of these processes at bottom have atoms, and beneath that, quantum processes going on. And that stuff might scale up, conceivably, in a functionally relevant way. So Penrose's is not the only, I know it's a great sort of pole to direct arguments against, but I would just suggest that Penrose could be wrong, but quantum processes could still conceivably play a role.
No, that's an interesting viewpoint. Yeah. So it's really again, it comes down to what level do you need to simulate things on. So regardless of coming up with actual mechanisms by which quantum processes might be happening, you just do need to draw a line between, can we simulate it fully classically, or do we have to start going into the quantum mechanics?
Can I ask
Sorry.
a question about going back right to the beginning of that superconducting loop? Is that an actual quantum system? It's not a physical model, a simulation of a quantum system that happens to...
It's an actual quantum system.
Is that by virtue of the fact that it's in superposition?
And it's the interesting thing about the flux qubit is that all the electrons are in the same quantum state. So you've got quite a large mass of object in a superposition of states. So that's why I think it's an interesting system, because if you can just make more of these and get them entangled, you can push your mass up.
Well, I think actually that's, sorry to go back, but I think that's actually a great illustration of the difference between what Penrose is getting at and other possibilities. In that you're talking about this quantum system you've created that is millions or billions of times larger than the scale people normally think about when they think about quantum processes.